Dear friends, it is finally time to talk about the existence of the non-trivial solution of Pell's equation. The proof will consist of three steps. Well, first recall that Pell's equation is x squared minus ay squared equal to 1, and a is a positive integer, non-square integer, which means that it is not a square of another integer. And the first step of the proof will be to show that there exists an integer d such that another equation which looks like the Pell's equation but has d instead of 1 has infinitely many integer solutions. And this will be maybe the most difficult part. The second step will be to show that there exist two solutions of the equation from the first step, which also satisfy the congruence condition. x1 and x2 must be congruent modulo d, and y1 and y2 must also be congruent modulo d, where d is the same one as the one in the right-hand side of the equation. And the third step will be to finally show that from all of the above, it really follows that there exists a solution of the Pell's equation, a non-trivial solution. Let's proceed to the first part of the proof. We need to show that there exists an integer d such that equation x squared minus ay squared equal to d has infinitely many solutions. First, consider a region on the coordinate plane bounded by hyperbola and given by the condition that x squared minus ay squared, its absolute value is less than d. We do not know yet what d should we choose, so we don't know yet what d we should choose, so we'll choose it a bit later. All these integer points inside this region lie on different hyperbola defined by the equation x squared minus ay squared equal to d. Well, it's obvious that since x, a, and y are integers, then d calculated by the same formula will be integer. So there is a finite number of integer d such that their absolute value is less than capital D. And all the points inside this region lie on a finite number of hyperbola and satisfy a finite number of such equations. So what do we need to show in order to prove that for some d, the corresponding equation has infinitely many solutions? Well, of course, we need to show that inside this region, for some capital D, there exists infinitely many integer points. Points where x and y are both integers. In order to prove this, in order to show that for sufficiently large d, as it will appear, there are indeed infinitely many points, integer points, nodes of the lattice inside the region, we will consider a parallelogram with vertices on the edge of the region, on the boundary of the region, and sides of this parallelogram will be parallel to asymptotes of all of the hyperbola. Well, you may have noticed that all of the hyperbola have the same asymptotes obtained by putting the right-hand side equal to 0. So the equations of these asymptotes, they're not written on the slide, but they are x squared minus ay squared equal to 0. It's a couple of lines. The area of such a parallelogram with vertices on the boundary of the region and with sides parallel to asymptotes, the area of such a parallelogram is equal to 2d divided by square root of a. Let it be an exercise for you to prove this. It is an exercise from linear algebra course or analytic geometry course, but not number theory. So, we'll use this formula for the area. And now, remember a famous theorem which we studied not so long ago, called the Minkowski theorem, which says that if we have a figure which is centrally symmetric, like a parallelogram, convex, like a parallelogram, and with area greater than 4, which can be provided by choosing large enough capital D, then inside this parallelogram there will be an integer point other than the origin of the coordinate plane, other than 0, 0. So we understand that inside this parallelogram there is an integer point other than 0, 0. But we need not one point, we need infinitely many integer points in the region. So when we find such point in one of the parallelograms, we can consider another parallelogram, which is thinner and longer, thin enough so that the point from the previous parallelogram does not belong to the new parallelogram. It's outside of the new parallelogram. And inside this second parallelogram, there will also be an integer point, because area of this new parallelogram is the same. Actually, this formula for the area of the parallelogram holds for any such parallelogram with sides parallel to asymptotes and vertices on the dark blue hyperbola. And when we find a point in the second parallelogram, we can consider even thinner and longer parallelogram, such that points we have already found are outside this new parallelogram, and inside the new parallelogram there will also be an integer point, and so on, and we will every time obtain new and new points. So taking new parallelograms will give us new integer points. So therefore, there are indeed infinitely many integer points in this region if D is large enough. Where large enough, D, I mean the capital D, large enough means that the area of the parallelogram should be greater than 4 in order to use the Minkowski theorem. Of course, you might say, what if the integer point in one of the parallelograms lies on the asymptote? Well, in that case, well, indeed, we will not be able to find the parallelogram that does not contain this point. However, notice that slope of the asymptotes is irrational, because a is not square, and slope is 1 over square root of a, plus minus 1 over square root of a. From this it follows that asymptotes contain no integer points except for the origin point 0, 0. Therefore, in each parallelogram we find points, integer points, that do not lie on the asymptotes, and this provides the possibility to find a thinner parallelogram and find the new point in this thinner parallelogram, and so on. So, now we have a proof that for sufficiently large capital D, there are infinitely many integer points in the region, and these infinitely many points lie on finitely many hyperbola. Therefore, there exists one of the hyperbola, there exists integer d such that equation x squared minus ay squared equal to d has infinitely many solutions. Now let's proceed to the second part of the proof.